Welcome to another one of our lecture in our lecture series on design of structural steel connections. Today we will be looking at some more interpretation of design results in IDEA StatiCa. We are looking at the design of a beam column shear connection. In our previous two lectures, we first modeled our connection in IDEA StatiCa, applied the loads. In our last lecture, we looked at some design results and we made our structural connection safe with respect to the strength of bolts and weld and also with respect to the plastic strain limit. And today we will be looking at the design results or the analysis results obtained for plates, bolts and welds separately. We are continuing with the interpretation of design results. So this aspect we looked yesterday. We discussed how the results that were displayed here were the enveloping results. And for analysis, 100% analysis has been completed. The plastic strain limit in bolts is well within the maximum limit of 5%, and the utilization of the strength of bolts and welds are below 100%. So the bolts and weld that we are providing is sufficient to resist the shear force that we have provided to this connection. To look into detail the results of plate, bolt and weld, here you can find some options at the very top. Currently it is analysis, this tab is active here, and you can see that the load application is 100% complete. Now if we go to this plates tab here, we can see the results for individual plates. So let's see here. What this tab does is, this displays the result for the individual plates. You can see that the plates have been given some specific name here. For example, this name, this is the top flange of column. So this is bottom flange of column, this is column wave. That means our software has divided our column section into three different plates. One top flange, one bottom flange and one wave. Similarly, for the beam also it has divided it into three plates. Beam top flange 1, beam bottom flange and beam wave. And for the cleats that we are using, there are the two legs of each cleat on the front side and then cleat on the back side. So the software has divided our plate elements into individual plates, and for each plate it has given the results here. For example, if you look into this table in more detail, the material of each plate is 350 grade steel, where 350 is the yield stress of the steel plate material and 490 is the ultimate stress. Then it gives value of different headings here, if you can see here. So what are these? Let us see. First, FYD. This FYD is the design yield strength. So how we got this design yield strength? We discussed it in our last lecture also. We obtained FYD by dividing the yield stress of our plate material with the partial safety factor. So if you divide 350 by 1.1, you get this value of 318.18, which is given as 318.2. So the plate materials in our structural steel connection, whether that plate material be of the beam, the column or the cleat plate, this is the maximum permissible limit of stress that is allowed on these plate materials, and this is based on the grade of steel that we are using. So what we discussed in our last lecture was that if the equivalent stress or if the stress in our plate material exceeds this value of 318.18, then our material goes into the state of plastic deformation. There will be a plastic strain. So what will be the limit of this plastic strain? Based on the Eurocode that this software is adopting at present, the plastic strain limit is considered to be 5%. So TP represents the thickness of our plate here. The flange elements of both beam and column were 10 mm thick. The wave of column was 8 mm thick. The wave of beam was 6 mm thick. And the cleat we consider to be 8 mm thick. Now you can see here, based on the loads that we are applying, which is represented as L1, we find the equivalent stress in our plate material. So the equivalent stress, if you see here, the maximum equivalent stress is seen in our which element? You can see that maximum stress is seen in this element here. If you can see here, here 319.2. Okay, this allowable stress of 318.2 mm has been exceeded in this element here. Okay, let me choose another color. This plate element, this plate element, and this plate element. In all other plate elements, the allowable stress is, or the equivalent stress in our plate material is below 318.2 megapascals. Only in these three elements, the stress has exceeded 318.2 megapascal. So for these three elements, only this plastic strain is calculated in our second last column. So the plastic strain in our wave of our beam is 0.5%. The plastic strain in our cleat plate is 0.1%, and in another cleat leg is 0.1%. For all other elements where the equivalent stress is below this value here, the plastic strain is 0. Now we can see what it means by enveloping results. Yesterday I discussed how the results on the left hand side were enveloping results. That means, let's see here, what is the maximum value of plastic strain out of these three? Obviously 0.5. So this maximum value is displayed here. So that means it is only showing the enveloping results. So now this is about the analysis result for our plate. Now let's move on to weld. Okay, first let's move on to bolts here. If you click on these bolts, so how many bolts do we have here? First let us look at the diagram below. Let's look at this diagram below. So our bolts have been numbered 1, 2 and 3. 1, 2 and 3. If you zoom onto this diagram here, and if you, let's say that we are clicking on bolt 1 here, bolt 2 and bolt 3. So when we are clicking on bolt 1, so this bolt is highlighted here, and similarly you can see the results for all bolts. So how is the software displaying the results? Okay, let's see here. So it has, if you want to see the detailed calculation for each bolt, you may press on this plus sign at the very front. For example, I want to see the detailed calculation of bolt 1 here. So I click on this plus sign here. So and the result is displayed here. Okay. Let me just increase this side here and see the displayed results here. First let's look at the summary of these results. For bolt 1 is under the tension of 2.6 kilonewton here. So we discussed in our last lecture, since only a downward shear force was acting in our connection here, this tension was not expected. We expected our bolts to be only under the action of shear forces, but due to the deformation of our cleat, some minimum amount of tension forces are being induced in our bolts, and this 2.6 kilonewton tension force is induced here. And then we have the shear force that is acting on our bolt here. So what was the value of shear force? We were designing for a shear force of 150 kilonewton. So if we assume that this shear force of 150 newton is taken equally by all three bolts, then the expected value of shear force in each bolt is 50 kilonewton. Now you can see here for first bolt, what is the total shear force that is acting? If you add this 25.2 plus 25.2, it's equal to 50.4. Similarly for other bolts also, for the second bolt, if you add this 24.9 plus 24.9, you get to be 49.8, and for this third bolt we get 50. So it's almost equal. That means while doing manual calculation, we assume that each bolt takes an equal amount of shear force, that is 50 kilonewton, and by software also we are getting almost same value of 50 kilonewton. So what is this slash means? What does it mean by 25.2 over 25.2? So this representation in IDEA StatiCa means that our bolts are under the action of double shear. As we discussed during our manual calculation also, for this connection that we are designing, the bolts are under the action of double shear. So if IDEA StatiCa directly gives you this 50.4 kilonewton value, then that means it's single shear. And if it gives in this way, by separating these two shear forces with a slash, then it means the bolts are under the action of double shear. So the total shear force acting on bolt 1 may be obtained by adding these two values, 25.2 and 25.2. So what is the capacity of our bolt in shear? We got it to be 94.1 kilonewton. So what is the utilization ratio in tension? Our utilization ratio in tension, we got it 2.9%. How did we get this? If you look at the detailed calculation below here, we saw that the tension capacity of our bolt was 90.4 kilonewton, whereas the actual tension that is coming onto this bolt is 2.6 kilonewton. So what happens if you divide 2.6 by 90.4 in percentage? How much do you get? Let us calculate this. 2.6 divided by 90.4. So you get this to be 2.87, which is nearly equal to this utilization ratio of 2.9. Similarly in shear, what do you get? If you look at the detailed calculation below, here you can see that the utilization ratio in shear is 53.5%. If you want to look at the detailed calculation here, just go down and you can see here. You can see that the shear force that is acting on our bolt is 25.2 kilonewton, and the shear capacity of our bolt is 58 kilonewton. So what happens if you divide 25.2 divided by 58 in percentage? How much do you get? 25.2 divided by 58. Okay, this you get it to be equal to, let me calculate, 43.44%. 43.44%. So we got here 53.5. So let me just see what is happening here. So this is utilization in shear. Okay, what is happening here is, let's see here. So what is the So what will be the bearing utilization in bearing? Let us see that. You can see here for bearing we have a bearing force of 50.3 kilonewton, whereas the capacity in bearing is 94.1 kilonewton. So what happens if you divide 50.3 divided by 94.1 into 100? What percentage do you get here? You get this to be 53.45. 53.45. That means nearly equal to 53.5%. So you can see here, out of these two ratios, the critical one is in bearing, because in bearing the utilization ratio is higher. Hence, instead of not this 43.44, but the software is displaying 53.5%, which is calculated as the utilization ratio in bearing. And finally, the last column, what it does is, the last column is utilization in combined tension and shear. And how do you calculate this? We calculate it by this formula here, as we have seen here. So this formula is used to calculate the combined bearing ratio, the combined utilization ratio in tension and shear, which we get to be almost equal to 29%. So this is how it is calculating these different values here. Similarly, you can see all the design results calculation for our second bolt and the third bolt. So one interesting thing what IDEA StatiCa does is, let me go to the initial calculation here. Okay. One interesting thing that IDEA StatiCa does is, when it is doing the bearing resistance check here, we know that this capacity in bearing is determined by this formula here, 2.5 kV dt Fu. We have discussed this formula many times also. And in this, how do you determine kV? We determine kV by this formula here. We determine these four values and we take the minimum value of these four. Now to determine these four values, if you see here, so E is the end distance, this is taking as 125 mm, and pitch it is taking as infinity. So what is happening here? This is for first bolt. So if this is our cleat plate, we have bolt number 1 here, bolt number 2 and bolt number 3. So for bolt 1, the end distance is being taken as 125 mm and the pitch is being taken as infinity. So what is happening for bolt number 2? Let us see. If you see here, now the end distance is being taken as 175 mm and the pitch is being taken as 50 mm. And finally for the third bolt, let us see at the design results for the third bolt. Okay, let's see here. These are the values. The E is being taken as 225 mm and pitch is being taken as 50 mm. So in our manual calculation, what would we have done? We would have taken pitch equals to 50 mm for all bolts. And what end distance would we have taken? The end distance would be, so what is end distance? End distance would be taken as this distance here, from the center line of our bolt to the edge of our cleat plate, which would be, I think we have taken this as 30 mm. So for pitch, what software is doing is, for pitch, since this is the first bolt and above this bolt there isn't any other bolt, the pitch is being taken as infinity here. So this is the difference that the software implements when it is doing the design calculations. And for the second bolt, obviously since we have taken this distance as 50 mm, it is considering the same 50 mm. And also the for third bolt, since we have taken this distance as 50 mm, it is considering 50 mm. And finally this was also 30 mm and we modeled a total cleat length of 160 mm. Now how is this end distance being taken? Okay, we get how this 175 mm end distance came. It is this 125 mm plus this pitch distance 50 mm. This we get 175 mm. And we also understand how this 225 mm came. It is this 175 mm plus this pitch distance of 50 mm. This comes out to be 225 mm. But how is this 125 mm being taken? Actually, if you look at our beam here, this was our beam. We had a cleat plate here. And what distance did we have 3 bolts here. And if you remember our previous lecture, or you can revisit that lecture also, what was happening is, to put our cleat plate at the center line, we were making some dimensions. We were calculating some dimensions, and what we found was that the dimension from here to the top of this flange would be 105 mm. Okay. And from this 105 mm, if we subtract the thickness of our this beam flange here, which was a thickness of 10 mm, we get this to be 95 mm. And then we know that the distance between this edge of our cleat plate to the center of our first bolt is 30 mm. So what happens if we add this 30 mm here? This 30 mm comes out to be 125 mm. So this is how the software is calculating the edge end distance. Rather calculating it from the edge of our cleat plate here, it is calculating from the edge of our beam here. From this, excluding the thickness of our flange, it is calculating the distance from this end of our beam. So this is the difference that the software is implementing when designing for these bolts or when analyzing for these bolts. And one reason why it is taking the end distance in this way is, if you look at our code, I have just opened the code. If you look at our IS 800 code here, and if you look at the definition of our end distance, so what it says is, for the definition of edge and end distances, what it says is, the edge distance is the distance at right angles to the direction of stress from the center of a hole to the adjacent edge. So if this is our cleat plate here, our stresses will be in the downward direction, in this direction. So if we wish to calculate edge distance is calculated at right angles to the stresses. That means this distance here. But the end distance is calculated in the direction parallel to the direction of stress. So this is our end distance here. And how does it define end distance? The end distance is the distance in the direction of stress from the center of a hole to the end of the element. So maybe because the definition says to the end of the element, and since these holes are being made in our beam element, then it is considering the distance up to the end of our beam element here. So these are some of the differences that this software assumes. So these are for the calculation of bolt results, and finally let's go to the results of our weld. The calculation of weld result is a little different compared to what we do. So why is it different? It's different because, and the verification of weld results are also quite complicated, and it is because of the finite element modeling approach that our software implements. Finite element modeling approach. So this means our welds that we have modeled there are divided into different elements, and the stress is calculated for each element. For example, let's see in our beam element here. In this beam element, okay, not beam element, let's see our cleat plate here. What was the thickness of our cleat plate that we assumed? Let me just rotate this. So what was this, not thickness, what was the width of our cleat plate that we assumed? This we assumed to be 65 mm. So we can see these results along the length of our cleat plate also, but for simplicity now, since the width is lesser than the length, it is divided into lesser elements, so we are looking at the results here. So these are divided into, let's see, for a distance of 65 mm width, into how many elements is our weld divided here? Let's see here, 1, 2, 3, 4, 5, 6, 7, 8. So our 65 mm width of our plate is, or our 65 mm width of our length is divided into 8 elements. So the size of one element is approximately, so this comes out to be almost equal to maybe 8.1 mm. So what is happening here is, If you look at the code setup here, we looked at this code setup before starting the calculations. What is happening is code setup is, what we have said here is the minimum size of element should be 8 mm and the maximum size of element should be 50 mm. So these element means these are the finite elements, and because we have considered to be the minimum size of element is 8 mm, here also we have got the size of our element to be almost equal to 8 mm. So this is not less than 8 mm. Let's see what happens. Okay, let me just go to my code setup and instead change the minimum size of our element to be 10 instead of 8, and then click on OK, and then run the analysis again. You can run analysis either from design tab or check tab. Under check tab, just click on this arrow in calculate here and check stress strain, not buckling for now. I will activate this equivalent stress also and then zoom onto this element again. Now you can see that our weld element here has been divided into 4, 5, 6 elements. So 6 elements means it is almost equal to 10.5 mm for each element. So this is how we can change the minimum and maximum number of elements based on the degree of accuracy or degree of analysis that we require. Remember that the more you divide it into higher number of elements, the analysis time will be more. So that may be one thing that need to be taken care of, or that you may need to take care of that when doing this analysis in IDEA StatiCa. So what is this? This is weld 3 here. Okay, let's click on this weld element here. This is weld 3 here. Let us look at the design results for weld 3. So you can click on this and then you can see the results. So if you zoom onto this diagram at the bottom, then you can see currently I am selecting this second here. I am selecting this second weld element here, and this element is being highlighted here. Similarly, if I click the first one, then another edge is being highlighted. Let us look at the results of this 65 mm edge. Okay, in whichever side this may be, I am looking at the results for this element here. For this element here, which has a width of 65 mm. Okay. Now for this element, if you look at this right hand side here, what has happened is, since we divided it into finite number of elements, currently it is 6 elements. The permissible stresses or the stresses in our weld, the equivalent stresses are being calculated for all 6 elements separately. You can see these here, the graph or this bar diagrams are representing the stresses, and if you see here, you can see that these last 3 weld elements, these are the most stressed element, and the stress in these elements is, the maximum stress is equal to 224.4 megapascals. So this was the maximum stress in our weld element when we were dividing it into 6 elements. Okay, now let's see. Let's go to this code setup again. Let us see some differences that we observe. Let me go to this code setup once again, and let me change the minimum size of element to our default, which was 8 mm, and then let me calculate once again. Now let me select, I think this was our weld that we were looking at the results. Okay, this is our weld. Now this is divided into how many elements did we see here? 1 2 3 4 5 6 7 8. When we are dividing this into 8 elements, again these elements at the right hand side of this weld are maximum stressed, and the maximum stress value now is equal to 224.8 megapascals. Okay, and let me check once again for another parameter here. Let me say that the minimum size of element now is only 2 mm, and then calculate the same stress and strain. So these are the results here. Let me select the same weld again, and let me see the equivalent stress here. Now you can see if you look at the equivalent stress, now the maximum value of equivalent stress is 225.1 megapascals. So you can see that based on the number of elements that we are dividing it into, the maximum result or the critical result may vary. Although it is not varying by much for now, this critical result may vary based on the number of finite elements that we divide our weld element into. So it is in our engineering judgment to decide into how many number of welds should we divide our weld elements into, and how can we calculate the total equivalent stress or the single value of equivalent stress. You can calculate by averaging these values here. So how do we average these values? Okay, let us say that we take the weighted average. Let us say that for 6 elements the equivalent stress was coming out to be 225.1 megapascal, and for 4 elements it was coming out to be 72.7 megapascals. You can just carry out the weighted average. 6 into 225.1 plus 4 into 72.7 divided by 6 plus 4. In this way you can calculate the equivalent stress for the weld, and then you can get a single value. So this is about how IDEA StatiCa uses the finite element modeling approach when calculating the equivalent stresses in weld. Similar to bolts, if you want to see the detailed calculation, you can again click on this plus sign here. So if you want to look at the design results or the analysis results, it's the same. First, the thickness has been given, and then the length of the weld has been given 60 mm, and for this the weld stresses are calculated. Now we have seen that the utilization ratio for this weld is 99.5%, since this is very near to the permissible value of weld stress. So how do we calculate the permissible value of weld stress? This is the formula here. You can see the formula here. The ultimate stress of weld, which is 490 megapascals, divided by root over 3 into partial safety factor, which comes out to be, which is 1.25 according to our code, and this comes out to be 226.3 megapascals. And since the maximum weld stress is 225.1 megapascals, this utilization ratio comes out to be 99.5% when you divide 225.1 by 226.3. So this is about the design results for our weld. If you look at the weld design results when we were adopting manual calculations, if you go to our Excel sheet, what you can see is Well, let me go to that part where we were checking for weld. So if you look at this final heading here, check for welding for the cleat leg connected to column. There we adopted 4 mm thickness, or the size of our weld, not thickness, the size of our weld we adopted as 4 mm. So what is the size of weld that we have adopted here? Throat thickness 4.2 means we have adopted a weld of 7 mm. So let me change this 4 to 7 mm, and then you can see that the permissible weld stress is 226.32. Okay, we have already done that, 226.3. And also what happened is we only welded the cleat along its length when we were adopting manual calculation, and that was coming out to be sufficient. So the weld stress at the interface was 95.67 for our weld that is along the length of our cleat plate. So what is coming out to be here? If we look at the weld results for our, okay, I will select this first weld, and this first weld is along the length of our cleat plate. And if I look at the design results, the F stress is coming out to be 71.8 megapascals, or the, let us say, equivalent stress, not F stress, equivalent stress is coming out to be 71.8 megapascals. And in our manual calculation, this came out to be 95.67. okay, this is not millimeter, I think this is again Newton per millimeter square. So since this weld stress at the interface is less than the permissible weld stress, this was coming out to be okay. So some differences in calculation results, the design results may be seen for this weld, since the approach is different in IDEA StatiCa in our software here. So after looking at the detailed design results for our plates, bolt and weld, we have come to this end of our lecture here. So we have also completed now the design of our beam column shear connection. From our next lecture onwards, we will start with a new connection type. So till then, you may revisit all our lectures which are uploaded in our YouTube channel. And we'll meet again soon with our next type of connection. Till then, stay safe and thank you.